you good to get started here?
Yeah, got it. Okay, so my
sure,
talk.
yeah. So,
Never mind.
yeah. So Harry is going to be telling us a bit about matching graphs and Matroids here. So go right ahead.
Okay, I will start. So my topic will be some topics about in graph theory. So we will first introduce what is matching and some typical matching problems, and then we will introduce about matrix, and give a higher overview of every topic in the graph theory and other combinatorics concepts. Okay, so this is our project today. First, we will define what is a graph here. A graph, it is made of 2-point components. The first component, it is a set of vertices, and the second is edges. So as it says, like the edges is just like some segments that connects different points together. And just as example here, so if we have a point set with 2 vertices, that is U and V, and the only possible edge is just UV. And the bipartite graph is a special kind of graph that you can separate the vertex set into 2 parts. And it is a bipartite graph, it and only if for the left part R L and the right part R. There's no edges between the 2 points in the same set. So it is called a bipartite graph because you can just separate it into 2 parts. And now we will introduce what is matching. Matching is actually a collection of edges here, and so the collection must satisfy such property that no 2 edges share a same endpoint, and this is called matching. And so there's an example here. So this is still a trivial example that if a bipartite graph with L and R, it only has one valid edge, and this only valid edge is a possible matching because there's no two edges that share a same point. So there's a very typical problem for finding about matching. It is find the maximum size of matching in a graph. And we have different problems for bipartite graph and non-bipartite graph because matching means differently for these 2 kind of graphs. So we will first introduce network flow. Network flow is used to solve the bipartite matching. This is just find the maximum matching in non-bipartite graph. So flow network is kind of upper kind of directed graph. So directed graph is just like a simple graph, but for every edge in the graph, there's a direction. Like if we design a direction from U to V. In typical graph, you can go from U to V and go back to U and go back to V, whatever you want. But in a graph that is directed, you can only go from a certain direction. You can't just directly go back from the same edge because there's a certain direction. So a flow network, it has something more. So for each edge in the flow network, there's something called a capacity. So we can just imagine it as a kind of pipe network. So imagine that there's water work near Mendoza, and there's by some pipes, like it can send water to your apartment, to your taps. And so every pipe, it has its own size and length. So it has a capacity. Similar to the flow network. So similarly, for no flow network, every edge has its own capacity, and so you can just imagine it as a pipe network and very intuitive. So correspondingly, for a flow network, there are many flows. Flows, it actually describes how many water is in the pipe. So it also describes how many value is in a certain every edge. So because there's a capacity, so a flow, the maximum number of flow in a certain edge, it can't be more than the capacity of this edge. So and there's also a very important conclusion that the number of flow that the total number of flow that every node receives, could be no more than it actually should be the same as the flow that every node sent, except the source node and the destination node, and we called it as a sink node here. So there's also a corresponding maximum problem for flow network. This is the maximum flow problem. So if you are given a flow network, you need to find the maximum possible flow. And we will see that the problem is useful for solving the bipartite matching. So we can actually reduce bipartite matching to a maximum flow problem. So if we are given a bipartite graph, we can make some additions, like make some update on the bipartite graph and make it into a flow network, so that if we solve the maximum flow problem on the new network flow, we can also solve the original problem, that is bipartite matching. So if we are given like a certain bipartite graph and we separately divide it into a left part and right part, we can make such addition. So first, we add a source node and a sink node. So sink node is just destination node, and then we add edges from S to every node in the left part, and then we also add edges from all nodes in the right part to the destination node, that is T. And we also just don't make any, actually we should, but we just keep the original edges like between L and R. And then we will add capacity to each edge to make it into a legal network flow. So we assign a capacity 1 to every edge, including these 4 types of edges. You have 3 types of edges. And if we have algorithm to solve the maximum flow algorithm, max flow problem for this new flow network, we also solve the bipartite matching, because if we have such bipartite graphs here, and there's a super source node called S, a super destination node called T, and we assign edges here, and there are some original edges, and we also make some nodes here. And if we have a legal flow here, and the capacity is 1, of course. If we have a legal flow here, for every we just call it water or just call it flow. Every flow here, it must be sent to some certain node, and for every edge that has a flow right here, we can see it as a part of a matching. And because it doesn't share, of course, it doesn't share a single endpoint, because assume we have here there's 2 edges in the matching, and because it is matching, it also has a flow right here. It doesn't satisfy the problem it's not a legitimate flow network, because you see there's only 1 here, but it sends out 2 units of water right out here. So this is not legal. Because you can't just assign because here 1 is not equal to 2, of course. Now, after we have our max flow computed, we can just pull off the edges that have flow here and put it out, and it forms matching as we just proved here. So this is how we will reduce flow network, a bipartite matching to a network flow problem, and we have such a network flow algorithm to solve it, and yeah, just know there's a certain algorithm. And the algorithm name is called Edmonds curve. So now, because the algorithm here, it only applies for only the bipartite graphs. So there are certain graphs that is not bipartite. That is, we can't divide it into 2 parts and every point is independent in the left part or in the right part. And we need to, if we want to find the maximum matching in this graph, in the non-bipartite graph, we need a new algorithm to find it. So a key difference of bipartite graph and non-bipartite graph, it is the non-bipartite graph must have, no, not certainly. If a graph that is certainly non-bipartite, it must have an odd cycle. And if a graph has no odd cycles, it is a bipartite graph. It's very interesting property, because just take an example. If because for every cycle, this go from the left to right, right to left, and for each go over and back, this an even number of edges. So there must not be odd cycles in the bipartite graph. So we will introduce an algorithm called the Edmonds Blossom algorithm. So blossom here means the odd cycle. That is why we need a new algorithm for the non-bipartite graphs. And the logic of the algorithm is just like follows. So first, we search for augmenting patterns. So augmenting patterns actually is just like a kind of patterns that connect the match point and matched edges and the unmatched edges. And if there's a path, certain path here, and for example, if there's a path from here, and so here, and back here, you can just match this edge and unmatch the next edge, and for the next point in the path, for the next edge in the path, you just match this and just flip them over. So this is called augmenting patterns. And so first step is search for augmented patterns. And in this process, if we find blossom that is odd cycle, and we just combine shrink it into a single vertex. So this is realized by we create a new point, a new node here, and for every node that is not in the odd cycle but connected to at least one node in the odd cycle, we just connect the node to the new generated node, and then we delete all the nodes in the old cycle. It only deletes the old cycle itself, but it doesn't affect the connectivity of the original graph. So we can just do such things. And if we shrink as much as blossom as we can, it becomes a bipartite graph, and we can just run still run the same algorithm as we have done in the bipartite graph. So this is some detailed steps for blossom algorithm. So it starts with a simple empty matching, empty collection of edges, and it keeps finding the augmenting patterns. And the way is doing algorithms finding the augmenting patterns. You can just do it by breadth first searching or depth first searching anyway. It can also both find the augmenting patterns or all cycles. And if we detect all cycle, just apply the how we shrink the all cycle to a single point. And if we find the augmenting patterns, that is, we can expand our current matching. We can augment the path matching along the path as we just found. And so we just expand shrink blossoms and augment our current matching, and do it until we can't find our augmenting patterns. And the current M is just the matching that it's just the maximum matching. So now, we have both algorithms for the bipartite matching and the non-bipartite matching. But actually, these two algorithms, it only works for graphs. This is a very specific algorithm. This is not a very high level, it doesn't provide a high level view of everything in the graphs, and moreover, everything in the combinatorics. And there exists such thing called Matroid. And Matroid is a very interesting thing that it can describe not only graphs, it can also describe matching as well, and it can even describe matrix. And I will just show how it does. So we'll give a definition of Matroid here. Matroid is combined with a finite ground set and a collection of the subsets of the power set of the ground set. So this is very similar to the definition of topology, if you have know the definition of topology here. And it also has some axioms. So there are 3 axioms for the Matroid. The first axiom, it is non-empty axiom, that is empty set is not independent. Oh, sorry, I forgot to introduce the definition of independence here. So for the collected subsets of the ground set in the second component called I, we call them independent. And the second component, we call it the independent sets. That's how we describe And now we have three axioms for the independent sets in the Matroid. So first is non-empty axiom. So empty set is not independent. And the second is hereditary axiom. So if there's ever any independent set in the collection that and every subset of the independent set is still independent. This is called the hereditary axiom. And the second axiom is called the exchange axiom. So this is very interesting. So if we have two different independent sets, and one set is smaller than the other, then in the smallest there must be at least one element in the smaller bigger set, and it is not in the smaller independent set. If we union the element with the smaller independent set, it's still independent. So let's give some examples for matroids, like certain types of matroid. The first is kind of a very trivial matroid called a uniform matroid. Uniform matroid is just for every given given finite ground set and every given integer that's greater than 0. Independent set, you can just set all of the subsets of the ground set with size no more than k. It is independent. And you will find that it actually satisfies the three axioms. And there's also a graphic matroid. Graphic matroid is kind of matroid that is used to describe a graph. And the ground set of the graph matroid, it is the set of the edges instead of the set of vertices. And a set, like a collection of edges, it is independent if and only if it is acyclic. Acyclic means that there's no cycle in the collection of edges here. And there's also another matroid called the linear matroid. So if you are given a set of vectors and a set is the collection of vectors here, it is independent and only if the vectors they are linearly independent, just like what we have learned in the linear algebra. So you see that in here we use matrix to connect graphs and matrix, the vectors, and many things together. So we introduce another matrix called partition matrix. Partition matrix is used to solve the bipartite matching here. And the partition matrix, it is defined based on a given finite ground set. And we design partition the current ground set into k parts. And if we assign an integral bound, it should be greater than 0. If every part is assigned with an integral bound, and we define a set, it is independent, and if and only if for every side S. Let me think. So it is independent if and only if for every partition, the number of elements in the S is not greater than the integral bound of this partition. So we can select, just as the last line, so we can select at most the integral bound elements from each partition.
I think you finished now about 1 minute here. We're a little pressed on time.
Oh, actually, I would end it shortly. So the way that we are going to find the bipartite matching from material intersection is we build a separation. So we will build two matrices, and left matrix, we call it left matrix and right matrix. Left matrix is only satisfy the matching property for the left set, the left vertex set. That is, okay, I will just show the next slide. So the left matrix set is independent if and only if it satisfies the property of matching in the left vertex set. And the left-right matrix, it is independent if and only if it satisfies the matrix property, the matching property in the left-right set. It means that their two edges doesn't share a same endpoint in the right set, right? And if we do a kind of thing called the matrix intersection problem, that is and we find the maximum independent set for both the matrix, and we will find the bipartite matching because it satisfies both the property for matching in the left set and right set. So this algorithm to find the Matroid intersection. So this is very similar to the Edmonds Blossom algorithm. So it's just like we start as an empty set and we augment our current set and expand it until we can't find more algorithm. And because of the exchange axiom, we can, if our current set is not a maximum, we can of course find another element that's not in our current independent set. And if we add this set into our current maximum independent set, it's still independent. So this is how we find the Matroid intersection, find the bipartite matching by the Matroid intersection. And this provides us even more powerful algorithm, higher overview of the current bipartite matching, not only only for bipartite graphs. So this is conclusion for our talk today. So first we introduced the bipartite matching. Then we introduced we solved it by network flow, and then we solved the non-bipartite matching by Edmonds Blossom algorithm. Then we introduced the Matroid, and by Matroid we have such algorithm called Matroid intersection, and it helps us find the maximum bipartite matching, but in a different and more powerful way. And this concept is very useful, actually even practical. So this is our talk today.
Yeah, and sorry about the timing limitations there. I checked to see if we have the room until a little after 4, but unfortunately a group is coming in